Again, welcome to Mathematical Structure for Computer Science, CS 113. And this is a discrete mathematics course. In this lecture, we're going to discuss about the growth of functions. So our main objective is to go through what we call the BigO notation and also BigO estimate for important functions, and big omega and also big theta notation. Again, normally we use the BigO notation again to analyze our algorithm. That's to find out how fast the algorithm is. So in the previous section, we discussed about what is an algorithm, and also we introduce algorithm that solve a problem such as searching and sorting. In this section, we will study again the normal operation used by these algorithms. This is a concept of again measuring how good the algorithms are or how fast the algorithm. Mostly in the computer science concept, there are two things that we always concerned about when we are developing an algorithm. Is the algorithm very fast enough? Or is the algorithm going to take more computer resources such as memory? So mostly again, fastness and memory. These are the two most important computer resources. In the next session, we're going to discuss about what we normally call the time complexity of an algorithm. But in this session, again, we're going to discuss about what is a BigO notation. So growth of functions. Here we say that in both computer science and also in mathematics, there are many times when we care about how fast a function grows. And this concept goes with how fast an algorithm runs. So in computer science, we want to understand how quickly an algorithm can solve a problem as the size of the input grows. So again, this is the whole concept of BigO notation. And the BigO notation again we use to measure how fast the function is growing, which again relate to how fast an algorithm runs. So here we can compare the efficiency of two different algorithms for solving the same problem. And for example, in a sorting algorithm we discussed, we saw different types of algorithms for sorting. Example would be a bubble sorting and selection sort. So here we can again measure these two algorithms. And when we are doing sorting, normally we are doing comparison of the list of the items that we are sorting. So the more comparison we do, I would say the slower the algorithm is. So we can again, the main goal here measure the fastness or the efficiency of the algorithm. So here we also say that we can also determine whether it is practical to use a particular algorithm as an input as the input grows. And there are some problems again in computer science that it's almost infeasible. It's not practical to use a computer to solve those problems. We will discuss that one in our next lectures when we talk about the time complexity concept. So two of the areas of mathematics where questions about the growth of function are studied is the number theory. And number theory is one of the topics in the discrete mathematics, and we are going to cover it in the near future. And also combinatorics, also another topic in discrete mathematics. So these are most of the two major areas in mathematics where we study about how a function grows or the growth of a functions. So BigO notation. Here we say the definition for a BigO notation is, and the whole concept here is that the growth of a function is often again described using a special notation. And this is notation is called again the BigO notation. So the concept of using BigO notation is to describe how functions grow or the growth of a function. we will see an example. So first, let's go through the definition. Here we said, let f and g be functions from the set of integers or a set of real numbers to the set of real numbers. So we say that f at x is, again, the O here means big O. So here we are saying that f at x is a big O of g at x only if there are constants c and k. We have constant of c and k such that f at x is less than or equal to c at g at x. So here we say always whenever x is greater than k. And we may discuss this in a few slides to come. And again, this is read as f at x is big O of g at x. Again, I use the term BigO notation again. So big O of g at x, or g. So the constant c and k, we normally use the term witnesses, or they are called the witnesses to the relationship. F at x is big O g at x. Again, only one pair of witnesses is needed always. So intuitively, the definition that f at x is big O g at s says that f at x grows slower than some phase multiple of g at s as s grows without bound. So again, that's the whole theory behind BigO notation. And we will see an example which hopefully may help us to understand the concept. So here we say if one pair of witness is found, remember witness can be C or K, that bear the relation to our expression or the function relationship. So here we say that if one pair of witness is found, then there are infinitely many pairs. Also, we can always make K or the C larger and still maintain the inequality. So yeah, we have f at s less than c at g at x. So any pair C prime with K prime where C less than C prime and K less than K prime is also a pair of witnesses. Since, again, f at x is less than or equal to C at G at x, and also is less than or equal to C prime G at x. And so this will be whenever x is greater than K prime and also greater than K. So here we may see f at s equal to big O g at s instead of f at s is big O g at x. So this is an abuse of the equal sign, since the meaning is that there is an inequality relating to the values of f and g for sufficiently large values of x. So here we can say that again, it's okay to write f at s belongs big O g at s because big O g at s represent a set of functions that are big O g at x. So I think the main thing we should go through is the whole concept. The example here will explain everything to you. So for example here, they say we should show that f at x equal to s squared plus 2s plus 1 is big O of s squared. The whole idea is that, for example, we are assuming x is a variable. S can be any value. Now we can see that from this expression, s squared plus 2s plus 1, when s value is very small, let's even assume s value is 0. If s value is 0, then 1 is very important. Our solution here will be 1. Now, if s value is 2, Yes, stay 1 is important because here we are going to get 4 plus 4, so 8 plus 1, 9. But imagine if S value is 1,000. If S value is 1,000, even 1,000 square is way bigger than 2 times 1,000, and even the 1 will be almost out. So that's why here we are saying that if I have S squared plus 2S plus 1, the BigO notation of this will be S squared, or it will be OS squared, BigO squared. And here we say that, okay, since when S is greater than 1 and S is less than S squared, then we know that 1 is less than S squared if S is greater than 1. So in this case, we can write S squared plus 2S plus 1 should be greater than or equal to 0, and it should be less than or equal to, again, the highest exponent is S squared. So here we get S squared plus 2S squared, and this is 1 plus S squared. And that will give us 4S squared. So here we can take C equal to 4 and K is 1. In this case, we can see the K and C is there, again, the coefficient. Because the witness showed that F at S is big OS squared. Now, if I'm solving this expression and the answer became, let's say, 4S cubed, then we prove here that the big O is not big O S squared. It's rather big O S cubed. Most of the time, the very simple way to say it is the highest exponent variable will be the big O, because as S increases, we will see that 2S and plus 1 will be a very small value. And as time goes on, we are going to again ignore it. So here we say alternatively, when S is greater than 2, we have 2S is less than or equal to S squared, which is true. Now, if X is 1, then 2S is greater than S squared, because we're going to get 2, S squared will be 1, and 2S will be 2. But anytime, and if it's 2, they will be equal, because if S is 2, 2 times 2 is 4, 2 squared is 4. So yeah, the condition is that when S is greater than 2, then the second term 2S will be less than or equal to. So when S reaches somewhere around 100,000, then 2S will be irrelevant. Also here we said that 1 should be less than S squared. Hence we have 2S plus S squared plus 2S plus 1 should be greater than 0. And also should be less than S squared plus S squared plus S squared, which will give us 3S squared. And here we can say that again. C is 3 and K is 2. So if both F at S is equal to S squared plus 2S plus 1 and G at S equal to S squared, these are such that F at X is big O G at X and G at X is big O F at X. Because if F at S is big O of G at S, then G at S also is a big O of F at X. Here we have two expressions saying that if F at S is, here you can see that the highest exponent for both are, again, the same, 2. As S increases, 2S plus 1 will be irrelevant. So here we end up saying that F at S is same as G at X. And here we say that the two functions are of the same order based on the exponent, the highest exponent. We will discuss more on this later on. Now, if F at X is big O G at S and H at S is larger than G at S for all positive real numbers, then we can say that f at s is big O h at x. Because here we say f at s is big O g at x. And h at s is larger than g at s for all positive real numbers. So then f at s is big O h at x. Also, if f at s is less than cg at s for x greater than k, and if h at s is greater than g at x for all x, now for all s, h at s is greater than g at s, then we can say that f at s is less than or equal to c h at s if s is greater than k, as the condition said here. So hence we can say that f at s is big O h at x. So here we say again, for many applications, the goal is to select the function g at x in big O g at x as small as possible, up to multiplication by constants. So using the definition of BigO notation, show that 7s squared is big O s cubed. Now we have to show that 7s squared is big O s cubed. So here we can say that when s is greater than 7, when s is greater than 7, we get 7s squared will be less than s cubed. Because what will happen is that if s is greater than 7, let's say we have 8 here, 8 cubed will be greater than 7s. But when s is 7, you see we get 7 squared times 7 is the same as 7 cubed. Now when s is 6, 7s squared will be greater than s cubed. So that's why we say when the s is greater than 7 going, that's when s cubed becomes greater than 7s squared. So here we're going to take c as equal to 1. Again, the value have to be greater than 7. So k equal to 7. As witness to establish that 7s squared is big O of s cubed. And the condition is here saying that if s is less than 7, then we're going to get 7s squared greater than s cubed. So the only time it can be big O of s cubed is when s is greater than 7. Then 7s squared will be, again, less than s cubed. So this means we have to make k 7, c 1, then we, as witnesses for the relationship of 7s squared is big O s cubed. Now, a question says, will c equal to 7 and k equal to 1 work? So let's show that n squared is not, we should know that n squared is not big O n. So suppose there are constants c and k for which n squared is less than or equal to cn. Whenever n is greater than k, then by dividing both sides of n squared less than cn by n, then n will be less than or equal to c, must hold for all n greater than k. And this will be a contradiction. So will c equal to 7 and k equal to 1 work? It will not work. This is a big O estimate for some important functions. Here they say we can use big O notation to estimate the sum of the first n positive integers. So we have 1 plus 2 up to n less than or equal to n plus n, which equal to n squared. Here our goal is to use the big O notation to estimate the sum of first n positive integers. So 1 plus 2 plus 3 up to n. it should be less than or equal to n plus n plus n, which will give us n squared. So here we say 1 plus 2 up to n is big O n squared. Taking that c is 1 and also k is 1. And using BigO notation to estimate the factorial. Again, factorial of a number means, a factorial of 5 means 1 times 2 times 3 times 4 times 5. So here, our goal will be the exponent of the number of times. So if I'm looking for a factorial of 5, then I'll multiply the values 5 times from 1 to 5. If factorial of 10, 1 to 10. So here we know that n factorial will be 1 times 2 times 3 all the way to n. It should be less than or equal to n times n times n times n throughout. So that n times n times n times n will give me n to the power n. Because we know 3 times 2 is 3 times 3. So this will hold if n factorial is big O n to the power n, taking that c is 1, k also is 1. And the reason why this old again, factorial means we are multiplying is the value. And that's the rule here. The previous one is Hardy. So average we get n squared. So if I'm writing a code in computer science to find a factorial of a number, again, most of the time we either we use the recursion or we use the loop. Our BigO notation will be whatever factorial of a number we are looking for. If it's 5, then we're going to have a 5 to the power BigO of 5 to the power 5. If it's 20, BigO of 20 to the power 20. So use the big notation again to estimate the log n factorial. Now here we are dealing with n log. So give me that n factorial is less than or equal to n to the power n in the previous slide. Then log n factorial will give us, since we have n to the power n, we use the log property, which will be n times log n. So log n factorial is the same as big O n times log n, taking c equal to 1 and k equal to 1. Again, here we are using the log property, n to the power n. So the power will come to the front, n times log n. So this is the description of the growth of a functions. A factorial is exponential. You can see n factorial. And we know normally a log function increases, but when you reach some stage, there's an increase, normally it stays constant. So we can see n log n almost the same as log n. Only things that n log n starts at higher point or increase faster because of n multiplied by rate. A constant value will be, in this case we say 1, it will be horizontal. If the constant value is, let's say 30, then we go to 30, draw a constant line, a horizontal line. And 2 to the power n will give us a linear function or linear increment. So useful big O estimate involve log, powers, and exponents. So here we say that if d is greater than c, and c is greater than 1, or here we say that if c is greater than 1 or less than d, then n to the power c is big O, n to the power d. But nd is not big O nc. Why? The main reason why, because c is less than d. Since d is greater than c, then n to the power c is a big O of n to the power d. since D is greater. So in the previous example, I cannot say, for example, n to the power 2 is a big O, n to the power 3 is a big O of n to the power 2. No, the power you have to at least increase by 1 or the same. So that's what we mean here. Now, second, we said that if b is greater than 1 and c and d are positive, then we say that log base b n to the power c is a big O nd. But nd is not log big O log b n base b n to the power c. It's not. Why? Because again, here we have b again is what? Greater than 1. And c and d are positive values or positive. Now, if b is greater than 1 and d is positive, then we can say that n to the power d is big O bn. But bn is not big O nd. Now, if b is greater than 1, if b is greater than 1 and less than c, then we can say b base n is big O c n, because c is greater than b. But cn, c to the power n, is not big O b to the power n. Again, here the reason why, because c is greater than b, and b2 is greater than 1. So we have the combination of the functions. This concept is same as college algebra. We may have two functions. One may be inner, one may be outer combination. So here, for example, if we have f1 at x is big O g1 at s, and f2 at s is big O g2 at x, then f1 plus f2, the two functions, f1 plus f2 at x is big O of the mass of g1 at x and also g2 at x, the mass. Now, if f1 at x and f2 at x are both big O g at s, then again, both f1 at x and f2 at s are big O g at x. Here they are separately. We have g1 and g2 for f1 and f2. But if f1 f2 is same as g at x, big O g at, then f1 plus f2 at s is big O g at x. And if we have f1 at x is big O g1 at s, and also f2 at x is big O g2 at s, then multiplication also the same concept. f1 times f2 at s is the same as big O g1 at s times g2 at x. So here we say if f1 at s is big O g1 at s and f2 at s is big O g2 at s, then f1 plus f2 at s is big O mass g1 and g2. So here we say by definition of BigO notation, there are constants c1, c2, and k1, k2, such that f at 1x is less than or equal to c1 g1 at s when s is greater than k1, and also f2x is less than or equal to c2 g2 at s when s is greater than k2. So f1 plus f2 at x will give me f at 1x plus f2 at x, which is less than or equal to f1 at s plus f2 at x. Now, separately, f at x, f1 at s plus f2 at x will give me the same separately c1 g1 at s plus c2 g at x, less than or equal. So this is the argument of it. So the next is the big omega notation. Here also we say if f and g are functions from a set of integer or the set of real numbers to the set of real numbers, we say that f at s is big omega g at x if there are constants c and k such that f at s is greater than or equal to c g at s when s is greater than k. And then here we say that f at s is big omega of g at x. The big O gives an upper bound on the growth function, while the big omega will give it a lower bound. So big omega tells us that a function grows at least as fast as another. So f at s is big omega g at s if and only if g at x is big O of f at x. Again, big omega will give us the lower bound. So we should, yeah, they say we should show that f at s equal to s cubed plus 5s squared plus 7 is big omega g at x, where g at s is s cubed. So the solution here will be f at s gives us 8s cubed plus 7s squared plus 5s squared plus 7 should be greater than or equal to 8s cubed, which is the g at x, for all positive real numbers x. And also it's also the case that g at s is equal to s cubed, then it will be big O of 8s cubed plus 5s squared plus 7. We also have the big theta notation. So here we say that let f and g be functions from the set of integers or the set of real numbers to the set of real numbers. The function f at x is big theta g at s if only f at s is big O of g at x, and f at s also is the big omega of g at x. So here we say that f is big theta of g at s, and also that f at s is of order g at x, and also f at s and g at s are of the same order. So f at s is a big theta g at s if and only if there is existing constant c1, c2, and k such that c1 g at s is less than f at x and is less than c2 g at x if s is greater than k. So that's example here. They say we should show that the sum of the first n positive integer is big theta n square. So our first positive n positive integer will be 1 plus 2 plus 3 up to n. And we have already shown that f at n is big O n square. To show that f at n is big omega n square, we need a positive constant c such that f at n is greater than cn squared for sufficiently large n. And summing only the terms greater than n by 2, we obtain inequality. So we get 1 plus 2 up to n should be greater than or equal to n divided by 2 plus n divided by 2 plus 1 plus all the way to n. So that will be greater n by 2 plus n by 2 plus n by 2. And in all, we get n squared by 4. So this will give us n squared by 4. Since we have, again, n times, in general, this section will averagely give us n by 2 times n by 2, which will be n squared by 4. So here we can say c should be 1/4. Then we can say that f at n is greater than cn squared for all positive integers, and hence f at n is again big omega n squared, and we can conclude that f at n is again big theta n squared if c is 1/4. So we have another example here. Show that f at s 3s squared plus 8x log s is theta big theta s square. So we write down the 3s squared plus 8s log s should be less than or equal to 11s squared for s that is greater than 1. And we can see that if s is 1, we get 11. 3 plus 8 log 1 is 1. So that's why we say the only way this value will be greater, 11s squared should be greater, or 3s squared plus 8 log s should be less than or equal to 11s if s is greater than 1. So if s is 1, we get 11. If it's 2 going, then we get more than 11. So here we say that 8x log s should be less than or equal to 8s squared. We are solving the problem here. We take 3s squared to the right. We subtract it from 11s squared, so we get 8s squared. Hence, we said, okay, 3x squared plus 8s log s is big O of x squared. And s squared is clearly big O of 3s squared plus 8s log s. Hence, 3s squared plus 8s log s is big theta s squared. So here also when we say that when f at s is big theta g at s, it must also be the case that g at s is also big theta f at x. So f at s is big theta g at s if and only if is the case that f at s is also big O g at x. And g at s is a big O f at x. So let's go through this exercise. We have 2 exercises here. Here they say we should show that s cubed is big O s4, but that s4 is not big O s cubed. Actually, we saw example like this previously. And so here we want to show that s cubed is a big O of s4, but s to the power 4 is not big O of s cubed. So since we know that s cubed will be less than or equal to s4 for any value that s is greater than 1, we know that s cubed is big O of s to the power 4. The witnesses will be c is 1, k is 1. Since we know that s to the power 3 always is less than s to the power 4 if s is greater than 1. So witnesses will be c is 1, k is 1. And on the other hand, if s to the power 4 is less than or equal to c n squared, then dividing by s cubed, s is less than or equal to c. Since this later condition cannot hold for all large x, no matter what the value of constant c is, we're always going to conclude that s to the power 4 is not big O s to the power 3. As we can see here, as s, we have s cubed and s4. As s increases, surely s4 will always be greater than s. If s value is greater than 1, if s value is less than 1, s cubed will be greater than s to the power 4. If it's equal to 1, then s cubed is the same as s4. But if it's greater than 1, so that's our witness. C is 1, k is 1. Then we know that s cubed is a big O of s to the power 4. Another example is we should determine whether s cubed is big O g at s for each of the following function given. So here we want to compare if g at s is s squared, so we want to determine whether s cubed is a big O of s squared, because g at s is s squared. And I think this is what we did previously. So we say no. The reason why, if s is greater than 1, s squared will be less than s cubed. So that is no. B, we have s cubed and s cubed. So you will say yes. S cubed can be less than or equal to s cubed for all x. But this time the k will be 0. C will be 1. And then we have s squared. Most of the time, we can use the exponent power. You see, s cubed and s squared is impossible. But here, g at s is s squared plus s cubed. The highest exponent is s cubed, so this is s cubed. So this is possible. And also here we get the c equal to 1, k will be 0. Now, when we go to C, so B also is possible, s cubed, as we said, yes. C is here. D also is possible because we have s to the power 4 is greater than s to the power 3. So that's what we said. S cubed should be less than or equal to s squared plus for all x. So witness will be C is 1, K is 0. Now let's look at E. E, we have 3 to the power x. This is a little bit tricky here. You see here we have s cubed, here we have 3x. So it depends on the value of x. If the value of x is 1 or less than, let's say less than or equal to 2, 2 cubed will give me 8, 3 square will give me 9. So that's why you can see the rule said here. Since s cubed is less than or equal to 2 to the power x, and is less than or equal to 3 to the power x, for all s greater than 10, thus we say that c is this, and c is 1, then k is 10. Because here the value of 3 to the power x and s cubed. Then the last section, we have s cubed by 2. It's also possible by here for all x. So s cubed less than or equal to 2 times s cubed by 2 for all x. So c will be 2, then k will be 0. Again, so this is the conclusion. Again, the main objective of this lecture is just to go through what is a BigO notation and the concept of trying to find out the BigO, also big omega, and also the big theta, the concept behind it. So wish everybody the best. Thank you.